This video is about electric current. We'll start by discussing how charge moves in a conductor, then we'll learn about direct current, and we'll finish up with drift speed. Let's begin with moving charge in a conductor. In an earlier video, we learned about positive and negative charge. In addition, we also discussed electric fields. When we place a charge in an electric field and release it, an electric force acts on the charge, so the charge moves. When charge moves, we say that there is an electric current. The movement of charge, in other words the electric current, is due to the presence of an electric field. Charge can move, so an electric current can be present, in solids, liquids, gases, and the vacuum. The most common example of an electric current in everyday life, and in this course, is a current in solids, more specifically metals. Wires in the walls of your house, your computer cable, and your phone charger are all made of metal components. So let's see how an electric current is created in metals. Let's take a piece of a cylindrical metal wire, magnify it, and examine what happens in the wire when no electric field is present, and how this changes when the wire is placed in an electric field, so for example, between a negatively and a positively charged plate. Our example is a simplified model of what actually happens in real life, but it should give you a good idea about how electric current is created. The exact structure of different metals vary, but what they have in common is that they are composed of positive ions that sit in fixed positions and electrons that are free to move. These electrons are sometimes called free electrons. When no electric field is present, the electrons move in a completely random manner. The arrows on the diagram show this random movement. When the wire is placed in an electric field, the positive ions remain in their fixed positions, while the free electrons start moving away from the negative towards the positive plate, since these electrons are negatively charged. During the process, the electrons collide with the positive ions. These collisions lead to a phenomenon called resistance, which we'll learn about in subtopic 5.2. This movement of charge is what we call an electric current. There are two types of currents that we'll learn about in this course: direct current and alternating current. We'll discuss alternating current in subtopic 5.2. Now, let's look at direct current. As we discussed, when charge flows, we have an electric current. There are two types of currents that we'll talk about in this course. The first is direct current, which we'll discuss here, and which is an electric current where charge flows consistently in one direction. The other type of current is an alternating current. In an alternating current, the direction in which charge flows switches back and forth at regular intervals. You will only learn about alternating current in more detail if you're in physics higher level. In the core syllabus, we only deal with direct current. As we saw earlier, when a piece of metal wire is placed in an electric field, charge flows in the wire. Since the direction of the electric field remains the same, charge keeps flowing in one direction, in our example here to the right, so we have a direct current. Let's see how to find the size or magnitude of this current. Imagine that we're standing at point P, observing the charge that is passing us. Let's assume that during t seconds, the amount of charge that passes us is q coulombs. To calculate the magnitude of the current in the wire, we can use this formula. Here are the variables for the formula. The SI unit of electric current is the ampere, denoted by capital A. The ampere is one of the 7 fundamental SI units. It is not actually defined as charge over time. The definition of ampere is based on ideas from magnetism. For now, we won't go into the details of this definition. Instead, we'll move on to learn about drift speed. Drift speed can simply be defined as the speed at which charge carriers move along a conductor. Here is the formula that can be used to calculate drift speed, and here are the variables. Let's explore this formula further. Once more, we'll examine the wire with the charge carriers moving from left to right. We'll assume that we're standing at point P. Given that the cross-sectional area of the wire is A, and that the charge carriers, in this case electrons, are moving at a speed v, the total volume of charge carriers that moves past point P in 1 second is A, the cross-sectional area, multiplied by v, the drift speed. Based on the variables table, the number of charge carriers per 1 cubic meter of the wire is n. Since the charge carriers in this example are free electrons in the metal, there are n number of free electrons in 1 cubic meter of this wire. Combining this with the total volume that passes point P in a second, so AV, we get that the total number of charge carriers that pass point P in a second is n times A times V. Finally, since the charge on each charge carrier is Q, the total charge that passes point P in a second is n times A times V times Q. As we have seen earlier, total charge that passes a point in a second is the current, which gives us the formula I is equal to n times A times V times Q. We simply have to rearrange this formula if we want to find the drift speed. Let's summarize what we have learned in this video. We began by discussing how charge moves in a conductor, and concluded that electric current is a result of moving charge. This charge moves due to the presence of an electric field, and that there can be an electric current in solids, liquids, gases, and the vacuum. We added that the most common conductors that we encounter in everyday life and in this course are metals, and saw that when no electric field is present, the charge carriers in the metal, which here are electrons and are denoted by red negative signs, move randomly. However, when we place the wire in an electric field, the electrons will all move in one direction. The positive ions, denoted by blue plus signs, are stationary in both cases. Then we moved on to discuss direct current, and define direct current and alternating current. Then we moved on to the formula that can be used to calculate the size or magnitude of the current, and added that the SI unit of current is the ampere, which is one of the 7 fundamental SI units. Finally, we learned about drift speed, which we defined as the speed at which charge carriers move along a conductor. We finished up with this formula that can be rearranged to calculate the drift speed. This completes our discussion of electric current. In the next video, we'll learn about potential difference.